I think last we discussed the full problem. Advertising expenditure. That is the problem we discussed. Right? So that day we were discussing simple regression. Today we will move on to multiple regression models. Multiple, so next topic, guys, continuation, next such topic. Multiple regression. So underneath you can take down this bit. When we have several predictor variables, when we have several predictor variables, and one response variable and one response variable. One response variable. We can go for the multiple linear regression model. We can go for the multiple linear regression model. Multiple linear regression model. First up and continue. We can extend the idea that we use, in simple regression, to get the multiple linear regression model. Multiple linear regression model. Right. So in short, we can call these MLR models, multiple linear regression models, MLR. Right. So now we know, right, simple model, right? So simple model is you take, only that part, right? One predictor, one response. So this plus the error term. So now we are having several predictor variables. So n predictor variables. So we extend the idea. Right? So something like this, we get the other terms, right? Beta 1 x1, beta 2 x2, beta 3 x3, beta 4 x4, and we also on up to beta n x plus the third. So these are the predictor variables. And in this case, beta naught, beta 1, beta 2, beta 3. So those are the values you need to find. Something earlier case, we got beta naught and beta 1. So now here you have several betas, right? So we have to find out. So if say there are 5 betas, then we need 5 equations to solve. Right. So we write down this bit. Right. The general format of a MLR model, is right. Now we can write y equals beta naught plus beta 1 x1 plus beta 2 x2 beta 3 x3 up to beta n xn plus the So without writing a lengthy formula expression, we can shorten this using the sigma notation. Beta naught we can write as it is. And the other parts from beta 1 x1 to beta n xn, if you take, this can be put in a summation beta I xi. Where does this dummy I starts at 1 and goes up to plus the same thing put with the sigma notation. Here, and beta I should be found from the data set given the data set given beta I. So these beta i's you have to find from the data set given, and these are called the regression coefficient. So these beta i's are called regression coefficient. Beta i's should be found from the data set given, and those beta i's are called regression coefficient. So when I say beta I, this is also included. This beta naught is also included. Okay, so without considering this multiple regression in an abstract way, so we'll take a simple case. We have two variables because one predictor variable we have discussed under simple regression. So we'll go for two variable case. So next para. Okay. The MLR model next para. The MLR model. The MLR model. MLR model. With two explanatory variables, the MLR model with two explanatory variables, will take the form, right. So y equals beta naught x, beta 1 x1, beta 2 x2. That's it, only two variables, say two explanatory plus there. So the same thing, if you want, you can put using the sigma notation also, but sigma notation is not needed because this is not that much lengthy. Okay? So if you want, we can try it. Right. So now here, how many unknowns are there in this case? Three unknowns are there: beta naught, beta 1, beta 2. Right. So we learn under simple regression, we learn to get those betas, we use the normal equations, right? Use the normal equations. So here also you can go for the same technique. So now in this case, we have three unknowns. In simple regression, two unknowns, beta naught and beta 1. So we had two equations. Now here we have three unknowns. So we should develop three equations. Okay, right. So we'll write down that. To get the values of, get the values of the regression coefficients, get the values of regression coefficients, get the values of regression coefficients. Regression coefficients. We have to get the system of, normal equations. We have to get the system of normal equations. Get the system of normal equations. Normal equations. Belum lagi lebih dia kan belum. Right. So just we'll recall how we got those and then we counted it. Right. So for simple regression model, y equals beta naught plus beta 1x plus the error term. So this is our simple regression model. So don't write it all there. Just to recall. So we need to find beta naught, beta 1. So we need to develop two equations. So first equation, how we get, we sum it up as it is, right? We sum it up as it is. So the first equation would be sigma y equals, this is a pure constant. So there will be n pieces, right? N data pieces. So when you use all the n pieces, this will be n beta naught plus beta 1, you take out, then you get sigma. So this is equation number 1. We wrote it in a different way, like n beta naught plus sigma x beta 1 equals sigma y. So this is the first equation, beta naught, beta 1 unknown. So then we need to develop another equation. So what we did, we multiply this equation by x. So we got xy equals beta naught x plus beta 1x squared plus the error term, right? So we'll remove this one. That's easy then. So we sum it up, sigma xy equals beta naught sigma x beta 1 sigma x squared. So then we wrote this as beta sigma x beta naught plus sigma x squared beta 1 equals sigma xy. So that is equation number 2. So the sigma x naught, sigma x squared can calculate. This also can be calculated. So here n known, sigma x can be calculated, sigma y can be calculated. So you have two equations, two unknowns, beta naught and beta 1 are the unknowns. So you solve these two, get the value. So that's how we did in the last class. Right. So now we have three features. So now we go for today's one. So now what is our model? Y equals beta naught plus beta 1 x1 plus beta 2 x2 plus the error term. So that's our model. So three unknowns are there, beta naught, beta 1, beta 2. So we need three equations. How do we get the equation? So what are the things we know? Now x1 will be given, x2 will be given, y will be given. So these are the values will be given, right? So to get the first equation, we sum it up as it is. So we get sigma y equals n beta naught. Beta 1 comes out sigma x1 plus beta 2 comes out sigma x2. So sigma y we can get n, we can get number of pieces. Sigma x1 we can get, sigma x2 we can get. So we get one equation. Then how do we get the second equation? Earlier case, what we did, as it is we summed up, we got one. Second equation, we multiplied by x. X was the predictor variable, right? Predictor variable. Now how many predictor variable we have? 2. So we can multiply by x1, we can sum it up. Another equation. X2 is also there. You can multiply by x2, sum it up, and get the third equation. Right? So the same idea, right? Since there are two x's here, you multiply this by x1, sum it up, you get another equation. Multiply by x2, sum it up, you get the third equation. Okay? So if you multiply this by x1, what you get? x1y. Beta naught x1. Beta 1 x1 squared. Beta 2 x1 x2. So now you sum it up. So here you get sigma x1y. Beta naught sigma x1. Beta 1 sigma x1 squared. Beta 2 sigma x1. So these values can be calculated now. So beta naught, beta 1, beta 2, and same way you can multiply this by x2, you can get the 1, 2, third one. Solve. Okay. අරකේම extension එකක් යන්නේ. අරක කලින් අදලා අපි ගානක් හදුවානේ. You multiply, you got. Now if you want to get this, what you will sigma y needed. So this column is there. So the sigma y you can get. The n needed, how many rows are there? So that is your n. Sigma x1 needed, x1 column is there. You add this, you get sigma x1. Sigma x2 needed. So column is there, you add this, you get sigma x2. So all these pieces are available. So you can get one equation. So for this one, you need to generate x1, y1. You need to generate x1, y, you have to generate. x1 already there. x1 squared is not there, so you generate x1 squared. x1, x2 not there, so you generate x1, x2. That total figure above, you can write down the equation. Right. Okay. But we are in a then we do a problem in it. Next paragraph, write down. The normal equations normal equations. The normal equations for the MLR model. Normal equations for the MLR model with two explanatory variables. With two explanatory variables. Two explanatory variables are obtained as follows. Are obtained as follows. Obtained as follows. So here, so what is this? This is the original model. So you take the original model, sum it up. Sigma y and beta naught. Beta 1 comes out, sigma x1, beta 2 comes out, sigma. So first thing, model sum. This one model multiplied by x1. This is model multiplied by x2. Right, so you take the model, sum it up as it is, so you get the first equation. Take the model, multiply by x1 and take the sum it up, you get the second model. Take the model, multiply by x2 and sum it up, you get the third. So these are the three equations you have to solve. So 3 unknowns are there, beta naught, beta 1 and beta 2. So we need 3 equations. So we have the 3 system of equations. So next, after the equations, you can write down this way. When a data set is given, when a data set is given, when a data set is given, the data set is given, we calculate, when a data set is given, we calculate the required, calculate the required sums, we calculate the required sums. Okay, so we mean these ones, right? The required sums. We calculate the required sums and develop the corresponding system of normal equations and the corresponding system of normal equations and the corresponding system of normal equations. Corresponding system of normal equations. And solve to get the regression coefficients and solve to get the regression coefficients. Solve to get the regression coefficients. Take an example. The following table example. The following table provides the systolic blood pressure. Following table provides the systolic blood pressure. Comma, age in years, and the weight in kilograms, For each patient in a ward, each patient in a First, assuming that the systolic blood pressure depends on age and weight of the patient, develop the MLR model using the normal equation approach. Develop the MLR model using the normal equation approach. So your data set. So the values are bit large values because it's the actual data, blood pressure, right? Maybe more than hundreds. weight maybe 60s, 70s. And the weight also the same way, yes, age also same way. So can't tell age, values are a bit large, but we'll go for this, then we know how to really calculate. So this is your data set. So when you take down the data set, leave maximum space on the right side because you have to develop several columns, X1, X2. You need to develop X1, Y, X2, Y, X2, Y, X2, X1, X2, and then X1, X2, X1 square, X2, right? So 6 columns you have to develop. So leave space, maximum space on the right side, and leave maximum space on the right side and take them. So they are on the other side. Now I have given the process, right? So what you need to do. So now see, here we have the name, real names, age, weight, blood pressure, but the model says X1, X2, right? And Y. So which one is your Y? Blood pressure is our Y, right? Because blood pressure depends on age and weight. It's given. So blood pressure is Y. Age is there, weight is there. So according to our convenience, we can take this as X1, this as X2, or maybe this as X2, this as X1. So our choice. So define your variables. Get the MLR model so that beta not beta what you have to get. Right? So to get this, identify the columns you need to develop. So I said you need to develop several columns here, right? You need the sums, right? So identify. Get the required sums. Get the normal equation. Solve the normal equation. Get the MLR coefficient. Write down the MLR model. So to get the MLR model, these things you have to do. That's a process. Right. So you take down this, then we'll just follow this sequence. Eleven pieces are there, 11 pieces. Copy the data, and then let me explain. So blood pressure we are going to take as Y. This is our Y. Age we'll take it as X. Okay. X1, X1. And weight we'll take as X2. Right, this X1, X2, if you like, you can change, no harm. If you want. Right. So now what are the columns we have to develop? So you need to identify from the equation, right? So here see sigma y needed, sigma y needed, y is there, no problem. So we need sigma x1 needed, x1 column is there, so we can get sigma x2 needed, x2 column is there, so we can get the total. So for the first normal equation, we don't have to develop any separate columns, right? We have all the required ones. Now, second one when you take, right? So no need to memorize anything. We look at the formula and decide what are the columns we are going to develop. So second one, x1, y column needed because the sum needed. So you develop that column x1, y needed. Okay, develop. Then here sigma x1 needed, x1 is there. Sigma x1 squared needed, we don't have that. So we'll develop that. X1 squared, so I'll put this way, x1 squared. And then we need sigma x1, x2, the product that is also not there. So we'll develop x1 into x2, right? So the required ones for the second normal equation we have developed. 3 columns needed, right? Then next third one, x2y needed. We don't have, so we'll develop x2y, okay? Then sigma x2 needed, x2 is already there. Sigma x1, x2 needed, so that one already we have developed, so no need. X2 squared needed, we don't have, so we have to create that, x2 squared. So those are the columns you have to develop. 5 more columns you have to develop. So how we identify? By looking at this formula, the 3 formula. So x, y. X1, y. So values will be rather big values, but don't worry. X1, y. 132 into 52. 143 into 59. So likewise, you get all the values. Put it that way, then it is easy. X1 square, we have X1 here, so squares of those values. So X1, 52 into 52, 3,900. 59 into 59, so likewise you get all the values. Then X1, X2, the product. X1 is here, X2 is there. Product, multiply, 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 get the values here. 52 into 75, right? So here I have made a mistake there. It should be 52 into 50. is x1 squared, right? X1 squared, 52 squared, 59 squared, 67 squared. This is 52 into 75, 30, 59 into 8. Write down. Next one, x2 into y, x2 into y. 72 into 132. You get all the values. And last one, x2 squared, 75 squared, 80 squared, 84 squared, until 94. So we have calculated all the values, required values. So values are a bit large, but this is the actual data set. So I don't want to change these values. That's why we have to take an as it is. Okay. So now we need the total. So all these totals needed. So we'll get all the totals. So now, after getting the total, so these are the totals, sigma x1, sigma x2. Now you have the three equations, so substitute the total in this. So sigma y instead of sigma y, this is sigma y, 1651 sigma y. Here n number of pieces, 11 pieces, 11 rows. Sigma x1 total is there. Sigma x2 total is here. So first equation done. So similarly, develop the second equation, third equation, then solve. So use your calculator and this is sigma y. I have to tell that y here. This is sigma y. Okay. So now, in the last class, we discussed how to solve a two unknown system of simultaneous equation using our cat. So now we have three unknowns. So in your cal, you have the option. So you go into that two unknown. So three unknown case you choose and give the three formula. So when you put it the other way around, right? This should come here, right? Equals that. This should come here. For a three unknown case, the general format for three unknown case, the general format would be something like this. A1x plus B1y plus B1z equals B1. Right, A2x plus B2y, the general format. C2z equals B2. And the last one is A3x plus B2, B3y plus C3z equals C3. So that's how the values will be. A1x plus B1y plus C1 equals C3. Right? A1, sorry, A2, B2, C2, this is D2. A3, B3, C3, this is D3. So this is a general format. A1x plus B1y plus C1z equals D1. A2x, B2y, C2z equals D2. A3x, B3y, C3z equals D2. use your so what are the values we're looking for? We can also be on 30 point. That will be around, okay, 30.102. Okay, so we'll go up to 2 decimal place. Beta 1, 0.8369. So shall we take that 7? 3 decimal place. So even if you go up to 4 decimal, it's okay, fine. Everything you go up to 4 decimal, it's no problem. So this is 8027. So we'll take that 3. If you have gone up to 4 decimal place, don't cut, just leave as it. Okay. Those are the values you are getting. Remember that is okay. 30.8.8. So, right. So yeah, I have written only up to 2 decimal place. So you can write up to 3 decimal place. So after getting the values, you write down the model. Right. So 3 decimal place will write. Okay. So this is your beta naught, this is your beta 1, this is your beta 2. So in the model, write down, substituting the value beta naught, beta 1, beta 2, get the model. Then we know the variable names. So Y is blood pressure, X1 is age, X2 is weight. So here I have written up to 2 decimal place. Since you have calculated up to 3 decimal place, you put down all the 3 decimals, right? So that's fine. So we have the model. Blood pressure is the 30.102 or something, like plus 0.84 something. Then, okay, so they're asking us what would be the expected systolic blood pressure SPP of a patient whose age is 68 and weight 60. So we have the model. So just substitute instead of age, substitute 68, weight, substitute, evaluate, expected. So we can forecast. So with this, we can identify what kind of effect is there, right, on blood pressure due to age. What kind of blood pressure, what kind of effect is there to blood pressure with age. So now here, the coefficient of age is positive. So when the age increases, blood pressure also increases because this is positive. Weight coefficient is positive, so when the weight increases, blood pressure also increases. Sometimes suppose if there is a minus sign or something here, minus 0.8 if we have, when the weight increases, blood pressure decreases. So if this is positive, if the coefficient is positive, when this particular variable increases, the y also increases. If it is negative, when the particular variable increases, y decreases. Positive impact, negative. So by looking at the values, we can. Right. So we'll answer that question. 68 and 84. So just substitute the corresponding value, get the BP. Just drop that. we should have one independent variable, one variable. Then for multiple regression, you need many independent variables. Functional variable. They like satisfaction variable. Satisfaction depends on several things. So how many variables? But here also blood pressure depends on several things. Depends on the age, depends on the age. Okay. So here we are talking about 2 points. We take many points. Many points. We are going to take this example. Many points. 2 variables. Many points. Okay. If you have more points, the model will be best one. Okay, so we'll move on to chapter 4. Probability. Probability. So why we need this probability first? Why we need this probability? Okay, right. There we can say there is a 80% chance of raining in the evening, 80% chance of raining in the evening. So why are we saying 80% chance? Because we are not sure, right? So if we know definitely if it will rain, then we'll say it will rain in the evening. Then we don't need that 80%, right? So when there is an uncertainty, I say when you are playing a game, we can say, right, 60% chance of winning, 40% chance of not winning, right? When you say 60% chance of winning, 40% chance is there, it may go on the other way around, right? So when there is an uncertainty, probability comes into play. So probability can be treated as a measure of uncertainty. When there is an uncertainty, then probability comes into play, right? So probability can be treated as a measure of uncertainty, measure of uncertainty, right? So probability is bit confusing sometimes, but if you get the basics properly, then it will be easy, right? So if you don't get the basics properly, then it will be hard. Okay, so try to get the basics properly, right? How to identify. So we'll be discussing distributions. So we'll be discussing about 3 or 4 distributions. So each distribution, okay. There are certain conditions. If these conditions are satisfied, okay, it belongs to type A. If these conditions are satisfied, then it belongs to type B. So you need to know those conditions. For this distribution, what is the condition? For this distribution, what is the condition? If you know those conditions, when the problem is given, so problem will be given as a story. So from that story, you have to identify whether, okay, these conditions are satisfied. Okay, then it belongs to this. So you have to know those basics properly, right? Those conditions for this distribution, these are the conditions. For this one, these are the conditions. Then easily you can identify. So the main issue is identifying the distributions. After identifying the distribution, everything is there, right? Ready-made. So you just substitute, get the answer. That's it. Okay. So identifying is the important part. Okay. So try to get the basics properly, then it will be easy. Right. So we'll write down and the probability. Probability can be treated as a measure of uncertainty. Probability can be treated as a measure of uncertainty. Probability can be treated as a measure of uncertainty. It can be treated as a measure of uncertainty. Right. Full stop, continue. Consider the following 2 statements. Consider the following 2 statements. Consider the following 2 statements. probability of raining in the evening. Probability of raining in the evening is 0.75. Probability of raining in the evening is 0.75. Second statement. There is a 75% chance. There is a 75% chance of raining in the evening. There is a 75% chance of raining in the evening. Right. So if you take both means the same thing. Right. Same thing. In the first one, we have given in a decimal form, 0.75. Second one, we have given in the percentage form. So both mean the same. If you give the value in the decimal form, you call it as probability. If you give it in the percentage form, you say chance. So we don't say 75% probability of winning or raining in the evening, right? 75% if you say it's chance. 75% chance, probability 0.75. 85% chance, probability 0.85. Right? So same value, if you put it as decimal form, we call it as probability. If you give it the percentage form, it's a chance. Okay, right. So both mean the same thing. So why we need this probability? When there is an uncertainty, probability comes into. Okay, so now say you are rolling a die. When rolling a die, what is the probability of getting number 5? The probability of getting number 5 when rolling a die. So we say 1/6. What is the probability of getting a head when tossing a coin? We say 1/2. So how are we assigning these values to probability? Right? So how come that 1/2? How come that 1/6? How we assign those values? So next para we'll write down. There are three approaches. There are three approaches to assign. There are three approaches to assign probabilities. There are three approaches to assign probabilities to an event. There are three approaches to assign probabilities to an event. One by one we'll discuss. First one, classical approach. First one, classical approach. Classical approach. Classical approach. Right. So underneath, you can put a hyphen and write down. After finishing that, we can talk to the second, right? Classical approach. Underneath, put a hyphen and write down. In the classical approach, probability is defined. In the classical approach, probability is defined as a ratio. Probability is defined as a ratio. Probability is defined as a ratio. Right. So how? So when you say ratio, there should be a top part and a bottom part. Now 3/7 is the ratio. 3 is the numerator part. This is the denominator part. So now they say in the classical approach, probability is defined as a ratio. So something like this, right? So how it is defined? Probability was so in the denominator, right, in the denominator, total number of possibilities. Total number of possibilities. Total number of possibilities in the denominator part. In the numerator part, in how many we are interested, in, that's how it is defined. So in the classical approach, probability is defined as a ratio. How it is defined? Total number of possibilities comes in the denominator, and in the numerator, in how many we are interested in. So that's how it is defined in the classical approach. So we'll take a simple example on this. Find the probability of getting a number more than 4. Find the probability of getting a number more than 4 when rolling a fair die. Find the probability of getting a number more than 4 when rolling a fair die. So we know when we roll a die, we got 6 possibilities. What are they? We can get number 1, number 2, number 3, number 4, number 5, or number 6. We can get normal ordinary die. So now we want the probability of more than 4. So more than 4, when you say 4 is not counted. So we can have 5 or 6. So totally there are 6. We are interested in 2. So probability more than 4. Probability more than 4 equals. We are going for the classical approach. Here, total number of possibilities we have 6. In how many we are interested in? We are interested in 2 of those. So 2. So here, now when you have this kind of expression, when you are giving the probability value, give it in the maximum simplified version. So here 2 over 3 can be further simplified to the maximum level as 1 over 3. So give it in the maximum simple version. So here we have used the classical approach. So when you go for the classical approach, no need to repeat the experiment, right? Even you do once, till you can apply this. We need only total number of possibilities in how many we are interested. Find the probability of getting an even number. Find the probability of getting an even number when rolling a die. Find the probability of getting an even number when rolling a die. Second example. Find the probability of getting an even number when ruling a die. Okay. So we are going for the classical approach. So probability, even number. So these are the possibilities. So we are interested in even number. So 2 if we get, we are satisfied. 4 if we get, we are satisfied. 6 if we get, we are satisfied. So totally there are 6. We are interested in 3 of those. So classical approach, total number of possibilities 6. We are interested in 3 of those. Can be further simplified. It will be 1 over maximum simple version. Yeah, 1, 2, 3, 4, 5, 6. 6 are there. We are interested in an even. So 2, 4, 6. So we are interested in 3 of them. Totally there are 6. 1 okay. So that is classical approach. In the classical approach, probability is defined as a ratio. Probability is defined as a ratio. How total number of possibilities in the numerator, in how many we are interested in. The next one, second approach. Second approach is relative frequency approach. Second one, relative frequency approach. Relative frequency approach. Right. So what is this relative frequency? Now, say suppose you are having a coin and you are tossing that coin 100 times. Right? One coin you are tossing 100 times. We'll say 60 times we got heads. Right? 100 times we tossed, 60 times we got heads. What is the probability of getting a head in that coin? 60 over 100. So that is relative frequency approach. We are repeating again and again. So that probability is for that particular point, right? What is the probability? So now this relative frequency approach we use when we repeatedly do the experiment. Earlier one, you don't have to repeat. Even if you do it once, yes, you can find the probability. But relative frequency, you have to repeatedly do. You don't have to do 100 times or 1,000 times. At least 2 times. More than once you have to do 2 times, 5 times, 1,000 times, 50 times, right? More than once you have to do. Okay. So this relative frequency approach is there when you repeatedly do the experiment. This approach we can do. Right? Okay. So underneath like a case, put a hyphen and write down. This approach is applicable. This approach is applicable. This approach is applicable when we repeatedly do the experiment. This approach is applicable when we repeatedly do the experiment. We repeatedly do the experiment. Krishna, continue. In the relative frequency approach also, probability is defined in the relative frequency approach also. Probability is defined as a Probability is defined as a ratio. Probability is defined as a ratio. Right. So how it is defined? Probability first, so now we choose as a ratio, right? So here total number of repetitions. Total number of repetitions, because you are going to repeatedly do. How many times you did it? That number should come here, right? Total number of repetitions. And here, total number of successes. Total number of repetitions in the denominator, total number of. So if you are tossing a coin 100 times, 60 times you got heads, what is the probability of getting a head in that coin? 100 should come here. 100 times you have done it. 60 times successes. So 60 should come. So relative frequency approach we can apply when we repeatedly do the experiment. So we'll take an example. A coin is tossed. Example, a coin is tossed 75 times. Coin is tossed 75 times. And 40 times we got heads. And 40 times we got heads. Coin is tossed 75 times and 40 times we got heads. First up. What is the probability of getting? What is the probability of getting a head? What is the probability of getting a head in that point? The probability of getting a head in that point. So now what we want? Probability. So PR, probability of getting a head in that point. PR, H, probability of a head. Right. So we are going for the classical approach, relative frequency approach. Total number of repetition. How many times we did the experiment? 75 times. We repeatedly. How many times success? 40 times success. So 40 over 75. So here again you can clearly see this can be simplified. So we'll that's the maximum simplified version. So here it is 15, you can top and bottom by 5 you can simplify. So it is 8 over. So relative frequency approach. So two approaches done. First one, even if you do it once, if you are doing it once, you can go for it. First one approach, classical approach. Relative frequency approach, when you repeatedly do the experiment, you can use it. Third one, subjective approach. Third one, subjective approach. Subjective approach. Third one, subjective approach. Subjective. Right. So we'll try to understand. After that, we'll write down. Right. Now, subjective approach is something like this. Now, suppose you have started a new business. Right? You have started a new business. Business is new, you don't have any previous data, but still you want to identify what is the possibility of making a profit, what is the possibility of, or what is the chance of making a profit. So in that case, if you have data, you can calculate the probability, but new business you can't, you don't have data. So what you can do is you can ask a person who has the knowledge on probability. Then by looking at various aspects of your business with his knowledge, he will come up with that. And with his experience, he will come up with the value. So that is called subjective approach, right? So you have started a new business, you don't have data, but still you want to identify what is the chance of making a profit. So a person with the knowledge on probability, by looking at various aspects of your business, with his experience, he will come up with the value. So that is called subjective approach. So two people, if you ask the same thing to do, they will come up with two different values, right? With their experience and all, right? So that means it is a personally biased approach. But if you don't have data, you have no choice. You have to go for it. Okay, so when we use this subjective approach, when we don't have data, we go for this subjective approach. So three different aspects. Only once you are doing it, classical. You are repeating, relative frequency. When you don't have data, subjective approach. So that means all things are covered, right? Anyway, if you want the probability, somehow you can get it. So underneath you write down subjective approach. When we don't have data, to calculate the probability, when we don't have data to calculate the probability, a person with the knowledge on probability, by looking at various aspects, with his experience, will come up with a probability value, First term. This approach is known as subjective approach. This approach is known as subjective approach. Subjective. So next same thing. Next thing. Though this is a biased technique, approach. Since we don't have data, to calculate the probability, we don't have any other choices. Okay, right. So for that, we don't have examples, right? So that by looking at various things, you come up with a value, right? So now, in probability, most of the time we use these terms, right? Experiment, outcome, event, sample space, right? So we said, okay, we are repeating the experiment, right? So what these technical terms mean? So there are some technical terms usually we use, or most of the time we use in probability. So there are four technical terms. So we'll look at those four technical terms one by one. So special terms or technical terms. Next small subtopic. Special terms or technical. Special terms or technical terms. One by one way. Discuss first one. Experiment. First step. Experiment. 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 So we'll try to understand first. After that, we'll write down in short. So experiment. Experiment means something like this. Something you do, the result is not known in advance. Right? Something you do, result is not known in advance. Right? It's an experiment, right? Say you are tossing a coin. When you toss a coin, right, you know either you will get a head or a tail. So what we mean here is exactly what you get, we don't know. Right? So you are playing a game. Okay, we know either we will lose or we will win, or maybe it will be a draw. We know one of those three we will get, but exactly what we get, we don't know. That is what we mean, right? So a process for which the result is not known in advance is an experiment. A process for which the exact result is not known in advance is called an experiment. So tossing a coin is an experiment. Rolling a die is an experiment. Playing a game is an experiment. So in life, most of the things we do are kind of experiment. Sometimes we succeed, sometimes we fail. Okay? So experiment means a process for which the result is not known in advance. Right? So you don't have to memorize those things. Just put in your own terms. Right? Experiment means okay, this is what we need. Okay, so I'm not going to ask define experiment or anything, right? So you should know what do we mean by experiment. So now under experiment, we are saying a process for which the result is not known in advance. Process for which the result is not known in advance is an experiment. Process for which the result is not known in advance is an experiment. Example, tossing a coin, rolling a die, starting up a business, that is also experiment, right? Sometimes we succeed, sometimes we fail. Tossing a coin, rolling a die, hitting a friend is also kind of experiment, right? Okay, so many things are like experiment. So experiment. The second one, outcome. So now we learn experiment. So we are tossing a coin. So when we toss a coin, getting a head is outcome. Getting a tail is another outcome. So when you take an experiment can give you different results. So each result is an outcome of that experiment. Right? Each result is an outcome of that experiment. So when you toss a coin, it has two outcomes. You are rolling a die, it has 6 outcomes. Getting number 1, getting number 2, number 3, number 4, getting number 6. You are playing a game, 3 outcomes are there. You may win, you may lose, or it can be a draw. Right? So outcome means any possible result of an experiment is the outcome of that experiment. Any possible result of an experiment is an outcome of that. Right. Any possible result of an experiment, any possible result of an experiment, a possible result of an experiment is an outcome of that experiment. Is an outcome of that experiment. Is an outcome of that experiment. Right. Example. Consider tossing a coin. Consider tossing a coin. Consider tossing a coin. Then within inverted commas, getting ahead is an outcome. Getting ahead is an outcome. Getting a tail is another outcome. Getting a tail is another outcome. Getting ahead is outcome. Getting a tail is another. Getting ahead is outcome. Getting a tail is another outcome. So it has 2 outcomes. Then the third one. Event. So underneath, first we'll write down, after that I'll explain, right? Event. Right. A single outcome and the event. A single outcome, or a collection of outcomes, a single outcome, or a collection of outcomes, can generate an event. Basically, event means what we are interested in. Basically, event means what we are interested in. It means what we are interested in. So now how it is defined? So first it says it can be a single outcome or a collection of outcomes. Last line says event means what we are interested in will be the event. Event means what we are interested in. Right. So now suppose you are rolling a die. You are rolling a die and you are interested in getting number 5. You are rolling a die, you are interested in getting number 5. Last statement, what does it say? What we are interested in is the event. According to that statement, getting number 5 is the event, but getting number 5 is one of the outcomes. So a single outcome generates the event. Okay, right. So now that single outcome or collection of outcome generates the event. Take the same example. You are rolling a die. You are interested in getting an odd number. Last statement says what we are interested in is the event. So getting odd number is the event. But that is a collection of 3 outcomes. Getting number 1, getting number 3, getting number 5. So collection of outcomes generate the event. So event means it can be a single outcome or a collection of outcomes. That's it. Okay. So what we want is the event. Right? So write down the question. Consider rolling a die. Consider rolling a die with 5 as the success. Consider rolling a die with 5 as the success. 5 as the success. That's the mission. Then continue. Then, according to the last statement, getting number 5 within Bhattacharya. Getting number 5 is the event. Getting number 5 is the event. But this is one of the outcome. This is one of the outcome. Therefore, a single outcome generates the event. Therefore, a single outcome generates the event. A single outcome generates the event. Next line. Consider rolling a die. Consider rolling a die. Consider rolling a die with an odd number. With an odd number as the success. With an odd number as the success. In this case, we'll write it short. In this case, getting an odd number is the event. In this case, getting an odd number is the event. So that is according to the last statement. Getting an odd number is the event. But this is a collection of 3 outcomes. So it can be a single outcome or can be a collection of. What we are interested in is the. So the next one is sample space. So after doing sample space, we have to do some examples also. With the example, we have to see at least at most. So I think we better start that in the next class. Heading the third or fourth one is sample space. Sample space. So we'll start from there in the next one. We'll write down and then do the example. Setting up the example.